Okay, so we were discussing how the Rutherford model said that the atom is mostly empty space. It has most of its mass concentrated in a tiny little dense core called the nucleus, which is positively charged. That's where the protons and neutrons are located. Most of the atom, empty space, nothing. The size of the atom, easy number to remember, 1 times 10 to the negative 10th meters in diameter. Rutherford figured this all out. And Bohr went on to verify this. But Bohr took it a step further. The Rutherford model didn't say too much about the electrons. But in this lesson, we're going to talk about the Bohr model, which took the Rutherford model a step further. And basically, it was all about how the electrons orbit that nucleus. You know, I remember learning once that the size of the nucleus compared to the size of the atom is roughly the same ratio as the size of a baseball compared to the whole Yankee Stadium, you know, where all the seats and stuff. Basically, it's about the same ratio. So somebody standing on second base holding a baseball, the size of the baseball compared to the size of the whole stadium is about same ratio as the size of the nucleus to the size of the whole atom. Think about that when you think about how Rutherford shot those alpha particles through. Imagine throwing another baseball through Yankee Stadium and you have one baseball floating in the middle above second base. What are the odds that another baseball, you know, would go near this first one? That's how hard it was to get those alpha particles to deflect. Anyway, Rutherford did a great job, but now Bohr takes it a step further when he analyzes these electrons. Bohr discovered that the electrons couldn't just orbit in any circles around the nucleus. The electrons would only be found in certain key circles around the nucleus. So, if this whole thing here is an atom, And this here is the nucleus. Bohr stated that the electron can only be found certain distances from the nucleus. It could be orbiting in this circle. It might be orbiting in this circle. It might be orbiting in this next circle. It might be orbiting in this circle here. The electron could be found orbiting here, orbiting in this circular path, orbiting in this circular path, orbiting in this circular path, but never, ever be found in the space between those circles. It's almost like the space in between the circles was like forbidden zones. And basically, each of these circles corresponded to a different energy level. The innermost circle, this circle here, was referred to as the ground state and was given a quantum number 1. So the innermost circle was the lowest amount of energy. And if the electron was found orbiting in that circle, the electron was said to be in the ground state. Quantum number n equaled 1. Now, if the electron was given energy, it can make a quantum leap. Again, very bizarre stuff. Because the electron would make a leap from one orbit to another orbit without ever existing anywhere in between the two. Again, it's called a quantum leap. And if the electron jumped out to this orbit, the second circle out, that was given quantum number 2, and that was said to be an excited state, because the electron had more energy out there. And then from there it could jump to even higher circles if it gained more energy. N equals 3, n equals 4, all the way up to n equals infinity. These are called excited states of America. No, true. Excited states. Now, when the electron made a jump to an outer circle, like right here, it had to gain energy to be at that higher energy state. And basically, the most common way it could gain that energy is by absorbing light energy. So basically, anytime an electron jumped to a higher circle, it had to be gaining energy, and it usually got that from light. So it usually got that by absorbing energy. So a jump outward was called an absorption. Because the electron was absorbing light energy. Now, on the other hand, if an electron made an inward jump, it lost some of its energy. So guess what it gave off? Light. And another way of saying that it gave off light energy, it emitted. So that was called an emission. So the question is, how did Bohr figure out that the light can only be at certain energy levels? I'm sorry, how did Bohr figure it out that the electron could only be at certain energy levels? And how did he figure out the energy levels of these circles? Well, Bohr figured this out by studying the light that either was absorbed when the electrons jumped outward, or emitted when the electrons jumped back inward. So let's look at its apparatus. Let's say we have a light bulb and connect it to circuit. Of course, it gives off light in all different directions. The type of light it gives off is white light. Also called polychromatic light. Many colored light. And eventually I'm going to draw something more in here, in this area here, but for now I'm going to leave that blank. And we learned how if you shine this light through a prism, when the light goes through the prism, it refracts due to a change in speed in the light as it goes into the glass. So if I draw a little normal line, the light ray always goes straight in through the normal line, never bounces off the normal line. However, it does slightly bend, and it turns out that not all the colors bend the same amount. Red light hardly bends at all. Whereas violet light, blue light, bends the most. And of course, you have all the colors in between. And then when each of those light rays exits through the glass, this time the normal is going to be like this way. This is the normal on the way in, this is the normal on the way out. And each light ray is going to have a slightly different normal because they're not going to all be exiting the glass at the same spot. But nonetheless, when those light rays go from the glass into the air, they speed back up and bend away from the normal. So this time they bend down even farther. And if you put a screen over here, you end up seeing a perfectly blended in rainbow where there's no gaps between the red, orange, yellow, green, blue, purple. It goes from one color into the next. So basically on the screen, let's see. And this here is called a continuous spectrum. And this whole process is called dispersion. When white light breaks into the different colors. Now, I'm going to end up tweaking this diagram. And if you guys want to redraw the whole diagram over again, you can. Or if you want to just kind of try to tweak yours, it's up to you. But basically what I'm going to do is insert a duplicate page. And this time, what I'm going to do is I'm going to put a glass tube and in the glass tube, there's hydrogen gas. And of course, you wouldn't be able to see it. I'm just drawing some blue circles there. You wouldn't really see anything, but inside there's hydrogen gas. You really can't see it. And when you put the glass tube of hydrogen gas in the light that's headed through the glass prism, something amazing happens. You no longer have a continuous spectrum over here. As soon as you put that hydrogen gas in the light that's going into the prism, basically a few of the colors over here disappear. I'm not exactly sure which colors disappear, but let's say, for example, let's just pretend that green light disappeared. And maybe the orange light disappeared. So basically, where there used to be those other colors, now there's just a dark spot. And sometimes they're called dark lines. Dark lines where there used to be colors. So when you have a full rainbow, but you're missing just certain colors, that's called, well, first of all, let's not name it. First of all, what happened to that light? We put the hydrogen gas in front of the prism over here, and then right away there's some certain colors missing. So those colors went into the glass tube, but they didn't come out. Guess what the hydrogen gas is doing with those specific colors? Not sure? Let's go back. Bohr studied the light absorbed by the atom when the electrons jumped outward, and he studied the light emitted by the atom when the electrons jumped inward. So, guess what some of the electrons that were orbiting some of those hydrogen gas molecules ended up doing when the light went through? Yeah, which way? Out. Some of these hydrogen atoms right here, when the light shined through, those hydrogen atoms would absorb some specific colors of light. And basically, when those electrons when those electrons absorbed those certain colors of light, the electrons would jump outward to more outer circles. So why were there missing colors? Because the hydrogen gas molecules, the hydrogen gas, was absorbing those specific colors of light. And what happens when a gas absorbs specific colors of light? The electrons jump to outer circles. So basically, if we took a close look at, one of those atoms, see that dot right there? It's going to be this dot right there. It's going to be that. And basically, here's the nucleus. And then we said the electron can orbit in certain distinct circles. And basically, what was the electron doing? Well, when the light went through, the electrons were absorbing certain colors and jumping out to higher circles. Only certain colors of light, though, were absorbed. The hydrogen gas must be absorbing certain colors of light, when their electrons jumped to outer circles. hydrogen gas, I'm just going to say is. When their electrons jump to outer circles. So basically, by analyzing these colors of light right here that we're missing, Bohr figured out the energy level values of these guys from here to here. So basically, we know that the energy of the light particles, the photons, is equal to Planck's constant times the frequency of the light. This is the formula we got from the photoelectric effect. So if we know what colors were absorbed, we know their frequencies, and if we know their frequencies, we know the energy levels that the electron was jumping out. So, let me just try to make this as simple as possible. By knowing what colors were absorbed, we knew what frequencies were absorbed. By knowing what frequencies were absorbed, we can multiply by Planck's constant and figured out how much energy was absorbed. And then by knowing how much light energy was absorbed, the energy levels of the circles were figured out. So let me give you some of these energy levels for the hydrogen atom. Here's the nucleus. Here's the ground state. Here are some of the excited states. this is n equals 1, n equals 2, n equals 3, n equals 4. Now, this is another little reference frame issue we need to talk about. We know that the electron in the ground state has the lowest amount of energy. You might think that that amount of energy might be referenced as 0. That might seem like the logical thing to do, because since this state here has the lowest energy, you might think that, that's 0 units of energy. And then if the electron makes a jump up to a circle a little bit out farther, it absorbed energy, so now it has more energy. It's a higher energy, so maybe the energy level out here maybe is like, 13, yes? And then if the electron even absorbed more light energy and it jumped out to an even higher circle, you might think that the energy level out here is like 15. Because if you go to a higher circle, the electron does have more energy. So this would be a logical way of doing it, yes? But that's not how it's done, ladies and gentlemen. Basically, at the highest energy level, n equals infinity. At the highest n equals infinity, the energy value assigned to that is 0 electron volts. Remember, electron volts is a little baby unit of energy. If the highest energy level is 0, and the inner circles have less energy than that, then guess what the deal is going to be with the energy of the inner circles? They're going to be negative. And the farther inward you go, the more negative it becomes. So basically, if you go down to n equals 4, n equals 4 is negative 0.85 electron volts. And if you go even lower yet, it has less energy, so it's going to be even more negative. So it's going to be negative 1.51. And if you come into n equals 2, it has even less energy, so it's going to be more negative, negative 3.40 electron volts. And the ground state, which has the lowest energy of all, is negative 13.6 electron volts. How did Bohr figure out what these energy values were? By studying the light that got absorbed. And by studying the light that got absorbed, using those frequencies, you can figure out the energies that were absorbed. And knowing the energies absorbed, these energy levels were figured out. Now, guess what happened when we come back to this. Let me insert a duplicate slide. If we come back to this here, guess what happened when the light was turned off and taken away? Now, I am giving you guys a simplified version of this. But basically, now we have this glass tube of hydrogen gas that has electrons that have jumped to higher circles. They have more energy now. They absorbed some of the light that came from the light bulb. Well, guess what those electrons in the outer shells eventually do? They jump back down. They jump back inward, yes? So as soon as you take the light bulb away, basically the spectrum over here collapses. But guess what you end up seeing on the screen? Exactly. The colors that were missing before. Because now that the electrons are jumping back down, yes, when they jump back down, what do? Give off light energy. And basically, the colors that were missing before are now going to appear. And again, I don't really think I have the colors correct. I don't think they really correspond to hydrogen. But nonetheless, I'm going to stick to what I was doing before. Which colors did I show missing before? Orange and green. So, like the orange and green would be the only two spots that appear. And everything else over here would be dark. So, you just have like two spots, orange, green. The colors that were missing now reappear. This is called not a continuous spectrum, because all the colors aren't there. It's not a absorption spectrum, because it's not that key lights were absorbed out. Guess what this one is called? An emission spectrum. So I just want to work out one example, and then that will be a wrap of this lesson. Okay. So basically, let's go to the back here. In a hydrogen atom, an electron jumps from n equals 4 to n equals 2. And then I want to ask you a series of questions about this single jump of the electron from 4 to 2. Okay. I didn't tell you it was a 5-part problem, though. Okay. Is light emitted or absorbed? What is the energy of this light photon? Answer in electron volts. What is the energy of this light photon? Answer in joules. What is the frequency of this light? And what is the color of this light? So, first off, is light emitted or absorbed if the electron jumps inward, Dan, from 4 to 2? It's going to be emitted. The atom's going to give off the light. So in this case, it's going to be emitted. Okay. Now, what is the energy of this light photon, electron, in electron volts, yes? So what we would have to do is go back to our energy levels, and we would have to look at 4, this value right here, and we would have to look at 2, and we'd have to subtract those 2 energy levels. Because if the electron dropped from 4 to 2, the energy of the photon that's released is going to be the difference in those 2 energy levels. So you could say that the energy of the photon released is going to be the final energy minus the initial energy, because we know when that electron drops down like this, a photon of light is going to be emitted. So the final energy level is going to be what? Negative 3.40. And I think we just really want the absolute value of these, you know. So it's going to be the absolute value of negative the absolute value of the difference, that is, negative 3.40 electron volts minus negative 0.85 electron volts. So you got to be careful because you're subtracting a negative, yes? And when you subtract a negative, it's just kind of like adding them, yes? Do you have a value for that? 2.55. So this photon over here is going to have 2.55 electron volts of energy. Then the next question says, well, how much energy is that in joules? So you have to remember the conversion. Actually, I think it'll be on your table of, constants. But 1 electron volt is equal to 1.6 times 10 to the negative 19th joules. So we're just going to have to do a conversion between this small unit of energy to this bigger unit of energy. So we got 2.55 electron volts. 2.55 electron volts. And you know the way I like to convert is by using the factor label method. I multiply by a fraction that has an overall value of 1. And since I have electron volts here, I want to get rid of the electron volts, so I put 1 electron volt in the denominator and 1.6 times 10 to the negative 19th joules on top. And since the denominator and the numerator are equivalent to each other, the overall fraction value is 1. And now when I multiply across, the electron volts here and the electron volts there cancel out. And what am I left with? 4.08 times 10 to the negative 19th joules. Just a little baby unit of energy, joules. So, what is the energy of this lightning photon? It was 2.55 electron volts. And in joules, what was it? Is that right? 4 point. Now the next question is, what is the frequency of this light? Well, if we know the energy of the photon of light and we want the frequency, anyone know what formula we're going to have to use for that? Exactly. The energy of the photon of light equals Planck's constant times the frequency of the light. So the energy of the photon of light, so we had that. What was that? What was the energy of the photon? No, in joules.
Oh, 4.08 times 10 to the negative
4.08 times 10 to the negative 19th joules. And I know I want to use the joules because my Planck's constant is in joules per hertz. So my Planck's constant is 6.63 times 10 to the negative 34th joules per hertz times frequency. So make sure you use your EE button, otherwise use your parentheses. And when you crunch this out, what do you get for the frequency of the photon of light that was emitted when the electron jumped from 4 to 2? Say that again?
6.15 times 10 to the 8.
Okay, wait a second. 6.15 times 10 to the 14th, right?
Mm-hmm.
Hertz. So now we know the frequency of the light that was given off of the hydrogen atom when the electron jumped from 4 to 2. And then the last question. So what was that value again? 6?
6.15 times 10 to the 14.
And then the last question is, what is the color of this light? And when you take the regions, you'll be given a chart, and you could just look to see which color has that frequency. You don't have to have this memorized. For the AP exam, you'd have to be given extra information. But if I look on this chart right here, 6.15 ends up being blue light. So when the electron went from n equals 4 to n equals 2, blue light was emitted. Now I do have a couple more things I was thinking of as we doing this, as we did the problem, that I need to add in. So basically, a couple more things. If you have your nucleus and you have ground state n equals 1, n equals 2, n equals 3, n equals 4, all the way out to n equals infinity, basically, sometimes you'll be asked a question like, if an electron jumps from, let's say, n equals 3 to n equals 1, how many different colors of light can it possibly give off if it jumps from 3 to 1? Now, you got to realize there's different ways for it to jump from 3 to 1. So, Each color of light corresponds to a different frequency. Each frequency corresponds to a different energy of light. Each energy of light corresponds to a different subtraction value between two levels. So here's the deal. If the electron was up there, it could jump all the way down, and if it made one complete leap from 3 to 1, then it would give off a photon with a decent amount of energy. But guess how else it could jump instead of going directly from 3 to 1? First by jumping from 3 to 2, and then from 2 to 1. So it could make two smaller jumps and go first from here to here, and then from there to there. So there's 3 different jumps shown there. So how many different lights could be given off? 3. One frequency corresponding to this jump, one frequency corresponding to this jump, and one corresponding to this jump here. So the answer is 3 different colors. Now, they might not all be in the same in the visible range. So I'm not going to say 3 different colors. I'm going to say 3 different frequencies. Because they might not be in the visible range, so you wouldn't necessarily call them colors. So why don't you try one now? Let's say you have the nucleus, and here is n equals 1, n equals 2, n equals 3, n equals 4. Let's up the ante. If an electron was at an excited state of n equals 4, if it was going to jump from 4 down to ground state, how many different colors of light, or I should say, how many different frequencies of light could possibly be emitted? I try to do it like a systematic way, so I don't miss any of them. So what'd you think? I'm not sure. Let me see what I get. 1 from here to here, 1 from there to there, 1 from there to there. But then if it jumps from here to here, it's now going to have to jump from here down to there. Or no. From there. Or no, from here to there. And then from there to there. And then if it jumped here, though, then it would have to make one more jump down. How'd you get 8? Okay. I think I got them all there. Do you see that? You got 8 also? Or what am I missing? Oh, wait, 4 to 3. But I got 4 to 3 right here.
And then from 4 to 2 and 2 to 1, and then from
I got 4 to 2.
4 to 3 and then 3 to 1.
I got 4 to 3. I got 3 to 1. See, you don't repeat any if you use one.
Oh.
See what I'm saying? 1, 2, 3, 4, 5, 6.
I got 6 now.
Okay. But wait, there's more. Ionization energy. If you want to get the electron to absorb so much energy that it jumps all the way out to n equals infinity, that's called the ionization energy. Because if the electron leaves the atom, then the atom's not going to be neutral anymore. And the atom, once it becomes charged, it's called an ion. So that's why it's called the ionization energy. So it's the amount of energy that an electron must absorb to jump to n equals infinity. Thus, leaving the atom. Usually the ionization energy is from the ground state, but they could ask you what is the ionization energy from like n equals 3 or something like that. The good news is, due to our funky reference frame, it's not all that hard to figure out what the ionization energy is from each level. For example, let's say you had a hydrogen atom and you had an electron in the ground state. If you wanted to ionize that atom and get the electron to jump all the way from n equals 1 all the way to n equals infinity, you would have to subtract the energy levels. Energy level at ground state, 1, and the energy level at way up there, infinity. Well, what's going to be the difference in the energy level of 1 to infinity? Well, look at your values. How much does it start off with over here? Negative 13.6 electron volts. What about if it jumps to infinity? 0 electron volts. So if you subtract those two values, easy enough, how much energy is it going to have to absorb? 13.6 electron volts. What would be the ionization energy from n equals 2? 3.4 electron volts. You see what I mean? It's how much energy it takes to jump from that level to n equals infinity. But it's an easy subtraction because n equals infinity has an energy of 0. Okay? And one last thing. The final thing, do you guys have to memorize these energy levels? No. On the regents, you're going to be given a chart which actually gives you the energy levels, yes? But on the AP exam, you actually need to be able to figure those energy levels out for yourself. Now, you're really not expected to memorize all of them. However, there is a handy-dandy formula which you could use to calculate these energy levels. En, the energy level of n, where n equals 1, 2, 3, 4, the quantum number, is equal to negative 13.6 electron volts times 1 over n squared. So n equals the quantum number, the principal quantum number. So n equals 1 for the ground state, and then n equals 2, and then all the way to n equals infinity. And if you want to know what the energy levels are, if you plug in that value, you can get the energy level. So for example, the energy level for the ground state is going to equal negative 13.6 times 1 over 1 squared. So what does that turn out to be? Negative 13.6 electron volts. If you wanted to know the energy level of n equals 2, the next one, you just put in the 2 for the n. And it's actually negative 13.6 divided by 4. Okay? All right. That's my story, and I'm sticking to it.